Hello, welcome to another Step 432 video. Today we're going to talk about nonparametric regression. And to sort of remind you where we are in the grander scheme of things, we're talking about supervised learning as opposed to unsupervised learning. And within supervised learning, we're talking about regression as opposed to classification. And within regression, previously, we had been talking about parametric methods, for example, linear regression. And now, today, we are going to talk about nonparametric regression. And I'm going to go away for now. Nope. Okay. So the two examples of nonparametric regression that we'll see today are what we call KNearest Neighbors and also decision trees. We're going to show two methods, but we'll see how there's kind of a central theme to how they work in comparison to parametric methods. Okay. Right. Okay, so let's say we have some data, and we're going to sort of stick to this nice one feature variable example because it's hard for me to draw in higher dimensions. But sort of as always, here's our x, here's our y, and this is what the data looks when we plot it. And what we said last time was that we were interested in this idea of estimating the conditional mean of y given x. That will be something that leads to good predictions. And what we did last time is say something like this, right? So we could have assumed that y was some function. We'll just do this. Of the feature and then plus some noise, right? So if we did that, I'm going to guesstimate that we would have gotten an estimated line something like this, right? And in particular, that line is this mean portion here, right? But that's not exactly good. We as humans can sort of look at this data and see that we probably should have assumed a different model, right? So instead, we could have done something like this. So we assume that y is a different function of that feature plus some noise. And again, this is the mean portion that we're most interested in. We would do some estimation, and I submit that the estimated regression, oh gosh, I can't draw straight. Sorry, I can't draw a smooth curve. Something like that. And that seems a little bit better, right? But you might be thinking, well, that's all well and good, but we've drawn a very simple we have a one-dimensional feature space here. We can eyeball it. We can say, yeah, that's something roughly quadratic. So we can basically be guaranteed to assume the correct form of the model. So that's pretty easy. But what if it wasn't the case? Like, what if we didn't know what we should assume here for what our model looks like? I would also note that I should probably square this term, or else that's no good. Or else we wouldn't have gotten that quadratic relationship. But anyway, it won't always be this easy, right? We're going to have more than one feature, and it won't be so easy to visualize and know how to, the features relate to each other and how to assume a good form of the model. So how do we estimate the conditional mean without making such a strong assumption? That's what we're going to do today. So what I have here so far is that data replotted, and we still want to estimate the conditional mean of y given x. And what I have written down here first is an idea. So the idea is that we could estimate this quantity with the average of the y values that we see where x is equal to the value that we're interested in. So say I wanted to estimate the mean of y at this value, I simply go up and, wait. There's a problem here. So there's no other data points that have an xi that's equal to x. So this won't really work. So let's erase that and think of a better idea. So you've probably already gotten there. But so what we want instead is the average of yi where xi are close to that particular value of x that we care about. So what do I mean by that? So let's say that I wanted to estimate the conditional mean of y at, I don't know, this x here, right? So let's say that I believe that x values that are close to this value live within, say, a region like this. So what I would do then is, I'm going to try this laser pointer feature that I never had before. I would say, well, this point, this point, this point, this point, this point, and this point, they're all in that region. So average their average their yi values. And I don't know, that would be, I'm just eyeballing it, maybe something like this, right? So that's the idea. So we want to estimate the mean of y at a particular x value. So to do that, round up all the data points we have with an xi value that's close to that x, and then average their y values. Pretty simple idea, but it works pretty well. So again, this is great. This is what we would want, but unfortunately, I don't think we're going to be able to do that. Okay. So moving on to KNearest Neighbors. So KNearest Neighbors basically does exactly that. So KNearest Neighbors says, well, if you want to estimate the mean of y at x, use the average of the yi values in, the average of the yi values that have, well, I have this complicated expression here. So what is this? So that's a bunch of math notation, but basically what this is, it's the k observations with xi nearest to the x in question. Okay, so honestly, sometimes I worry that writing this down is silly because it's confusing. Let's just go ahead and sort of look at examples of this. So what I have here is the same data, not the data we were just looking at, but a different data set, but that's not important. So I have the same data plotted 3 times, and each time I want to use KNearest Neighbors, but estimating y at a different x and with a different number of k. So in the first example here, I want to estimate the mean of y at an x of negative 0.5. So here. So these 3 green circled points, those are the points in the data set that have xi's closest to negative 0.5. You might notice I'm saying close and not defining that. If ever I say close and I don't define it, just assume the distance metric that you all know and love, which is Euclidean distance. We could change that, but we often won't. But so anyway, so now that I know the value, now that I know the data that have, now that I know the 3 observations in the data that have the xi values closest to the x that I'm interested in, I simply average their y values, and that gets me this point here. That would be my estimate. And then basically I repeat this process. So here we're trying to find the average of y when x is 0. So that's here. But now I'm going to use k as 5. So I'm going to use more neighbors. And that's the green circled points. And when I average their y values, I add up here. And then same thing on the right panel. Now I'm interested in x of 0.75, which is right about here. But this time I'm going to try k of 9. So I circle the 1, 2, 3, 4, 5, 6, 7, 8. I think there's like 2 points right here. This is in the book, and you can see the code. I'm pretty sure there's 9 points here. But anyway, if I average their y values, I get to be right here. Okay. But again, this might even be, this is what's happening. But now I want to look at, well, what happens if we just take a value of k and apply it across all possible values of x? What does this look like? It looks like this. So this is that same data. Again, plotted 3 times. Now, we see the dashed black curve. That is the true mean function. And so what we see here is k-nearest neighbors with 3 different values of k applied to this data. We see a very large value of k. I should maybe rewrite them because they're kind of small. So here we have k equals 25. Here we have k is 5. And here we have k is 1. Right? So let's maybe start with k is 1, which is a very extreme value. So that says, if I want to predict at, say, an x right about here, well, simply use whichever data point is closest, that is in their x values, which is here, and predict its y value, so we see this here. And then we do that across all possible x. And so this is our estimate of the mean function, basically. And you see it kind of wiggles a bit too much. I'm going to use this highly technical term a lot, which is wiggle. Which is, sort of when something irregularly moves up and down, but wiggle is a very useful term in machine learning. It just sounds really funny. Okay, and then so what we see as we go to the left, that is increasing values of k, we see that our estimated mean function wiggles a bit less, because now instead of averaging over one value, in the k is 5 example, we're averaging over 5 nearest neighbors, and in the k is 25 example, we're averaging over 25 nearest neighbors. So this is hinting at this idea of model flexibility, where k is 1 is a highly flexible model because it can wiggle a lot, whereas k is 25 is inflexible because it does not wiggle a lot. Okay, so we've been using this k value, but we haven't sort of given it a name. So previously, I meant to erase some of this and then write it along the way. Oh, well. So previously, when we were looking at linear regression, we had these beta parameters. And we sort of said, okay, we're going to assume this form of the model and then, quote unquote, fit this thing to data. And it returns, beta 0 hat, beta 1 hat, beta 2 hat, and beta 3 hat. So we call those model parameters. And they are learned from the data. But now we've seen an example of something different, which we call a tuning parameter, which is, for example, the k, that is the number of neighbors, in k-nearest neighbors. And so this is a little bit different because rather than, quote unquote, learning it from the data, although we sort of will, but when I specify k is 5, like here, well, that tells me how to get that estimate. I don't sort of, estimate a parameter from the data. I'm just saying, well, here's how we learn the mean function from the data. Now, eventually, the tuning in tuning, we will tune this parameter. That is, we'll try many values of k and see which one works best. So we will sort of learn it from the data, but if we don't think about going through the validation procedure, we're just sort of setting it and seeing what happens. So it defines how we learn instead of us learning it from the data. Okay. Just another few quick notes on k-nearest neighbors before we go on to trees. So sometimes people will say something along the lines of KNN is very fast to train, but it is slow to predict. They might even call it lazy, like it's a lazy learner. So this is the idea that, to fit k-nearest neighbors here, all we really have to do is say for k is 1, the quote-unquote fitting just happens by, well, memorize the data. So once you've loaded the data, you're fine. But then, actually k is 1 is a bad example. Let's do k is 5. Well, so let's say we want to predict at, this x value. So, well, now we need to search through the data, find the 5 nearest neighbors, then average, then make a prediction. So that's why we say that it's fast to train, slow to predict. In other words, like I said, it's lazy. So you say, well, I want to do k-nearest neighbors, and k-nearest neighbors come back and says, hey, slow down there. I'm not going to do anything until you tell me to make a prediction, as opposed to a linear model, which, it'll spit out the coefficients, and then we plug into those to make predictions. So it requires more computation at training, but then prediction is simple multiplication and addition problem. There's no searching for nearest neighbors. Okay. But that's a bit of a computational thing, but if you're interested, that's just a note there. So something we've really been glossing over is which features should we use? And I'm just going to sort of say, I don't know. So obviously, in this example, there's only one feature x, so we don't really have a choice. But in higher dimensions, we could just give all the variables to KNearest Neighbors, and it calculates the distances in those higher dimensions, and that's fine. But that might not be the best idea. But we're going to sort of push this off for a while. We're going to, for now, introduce methods, and then later on, we're going to come back to this idea of, well, if we're in a high-dimensional space to start, we might want to reduce that a bit before we actually use a method like this. And we'll sort of mention why, perhaps in the next video. So something I didn't talk about at all in this video is, what do we do with categorical features? Because let's say you have a feature that's like, it's a category like cat or dog. Well, what is the distance between a cat and a dog? I don't know. So we'll find when we get into R and I dig into this, essentially, we're going to do a dummy encoding. So instead of storing them as cat and dog, we will store them as zeros and ones in that case, something like that. Okay, so I mentioned briefly how to calculate distance, and I said, well, use Euclidean. But actually, you could pick whatever you want. So maybe you've heard of something called a Manhattan distance or a taxicab distance. That would be a different distance metric, and you could certainly use that. But out of the box, any KNearest Neighbors function that we use in a statistical computing environment is going to be Euclidean distance. So just the distance you think when you think distance. Something that might be bothering you is this notion of, well, wait a second. If we're in higher dimensions, which we haven't seen yet, what happens if the two different features are on wildly different scales? So let's say we had an x1 that ranged between 0 and 1, and an x2 that ranged between 0 and a million. Well, x2 is going to have a much bigger influence on the distance calculation. So this is something that I'm going to say, this is important, but we're going to put it off until later. So in the sort of back half of the semester, we're going to talk about sort of more practical things. And something we're going to talk about is data preparation and all the different sort of things you can do to your data to get them ready for these machine learning methods. And for example, scaling some of the features to be, say, have mean 0 and variance 1 is something you might want to do, especially with KNearest Neighbors. But for now, we're just going to say, that's a good point. We'll remember that for later. Okay, so that was our introduction to nonparametric methods. You sort of note that they don't have these tuning parameters. Instead, they don't make these. Sorry, they do have tuning parameters. They don't have model parameters because we don't sort of assume anything about the form of the model. We just sort of go ahead and make an estimation. Okay, so how about another way of doing this? So in KNearest Neighbors, we sort of developed this notion of finding neighbors, and that's certainly one way to define closeness. So you find the neighbors that are closest to you, those are the ones you're going to use. What if instead we wanted to use neighborhoods? That is, sort of chop up the space of X into, say, here's a neighborhood, here's a neighborhood, here's a neighborhood, predict the same value within there. So what do I mean by that? So let's say we have this data here, and I wanted to chop up the X variable right about here. So just visually, I'll do this. And then what I'm going to do, and I'm going to call this this will be the left neighborhood. This will be the right neighborhood. Okay, well then within those neighborhoods, I'm going to look at the average of those points. And if I wanted to then predict a new point, say here, well, I would predict that average. All right, so good idea. You might see an improvement we can do to this already, but we'll get there. We'll get there. So this is the idea of decision trees. And so I just note this sum of squares total here. It's probably a quantity you've seen before. It's just taking all of the y values in the data set and comparing them to just the grand mean in a squared error sense. But so what decision trees do is they find a split that minimizes this quantity here. And a split will be a combination of a feature plus a cutoff value. So now what I have is this expression that is two sums of squares. So here I have a sum of I in this n sub l, and that's what I'm going to call the left neighborhood, and that is defined by, in our sort of one-dimensional case here, x values less than some c here being a cutoff, so I should really call this c maybe. And then this expression here, this mu hat sub n sub l, well, that's the average of the yi in that neighborhood. So that's this blue line here. And then we have similar things on the right-hand side, except the right-hand side, the right neighborhood is defined by x greater than c. And then what I have here is the average of the yi in the right neighborhood. Okay. Right. Yeah. So that would be the notion of finding a split. We want a split that sort of really minimizes this quantity. This split does that. You could have considered instead splitting here, but then you could see that, well, we would maybe have done this average on this side of it. We would have done this average on this side of it, and that would have been not so great. So this is a good first split. I say first split because we're going to keep splitting. So the trees, what they do is they recursively partition the space. So, sorry, I keep flipping back and forth here. So back here, I think when I first, wrote on this slide and then moved on to the next slide, you were probably sort of, concerned. You're like, well, wait a second now. Why don't you also split here? Well, and then we can predict the average in this neighborhood and predict the average in this neighborhood, to which I say, bingo, that's the right idea. So basically, anytime we create a new neighborhood, we then again try to split within that neighborhood. And we just recursively do that, well, forever until I tell you how to stop, but that's the idea. In this particular example, you can sort of see right away that we should probably not keep splitting, but that's the idea. So what I have in this slide is just to indicate that with this new split, what this quantity is here is the sum of squares error. The sum of squares error, we would replace the original predictions in that neighborhood that we now resplit by this new two sums of squares for the two new regions that we created. I'm not going to dwell on the notation here because it gets really messy real fast, but I'm going to move on to say that we can write this much nicer, and also I'm going to illustrate how we can use multiple predictors. So unfortunately, I'm limited by a two-dimensional iPad here. So imagine we have x1 on this axis and x2 on this axis, and sort of like coming out the iPad at me are the data points. So the axis that's pointing perpendicular to the iPad is the y-axis, right? So I'm not particularly interested in the data points because I want to talk about how the partitioning works. So let's say my first split is on the x1 variable, and it's here. So that creates two neighborhoods, and it's only dependent on the x1 variable. So anything less than this x value is in one neighborhood, everything greater than is in another. But we can also split on other variables. So now we want to recursively partition the space. So we want to continue splitting in here, and we want to continue splitting in here. So let's say inside of here now we decide, well, let's split on that x2 variable now. That's a good split. And again, we want to find a split that minimizes this quantity within that partition. And maybe I get something like this. But it only splits within that partition, right? So now x values less than this and y2 values less than this, they all live in a neighborhood. x1 values less than this and x2 values greater than this, they all live in a neighborhood, and so on. And we could keep going. We could say, well, I want to do another split inside of here, so maybe we do something like this. and then we could split inside of these two, and we say, oh, let's do another split in here, and we find that the best split there is something like this. So now we've partitioned the space, and let's say we have n1, n2, n3, n4, n5 neighborhoods. But in general, then what you would do is, to make a prediction inside of any one of those neighborhoods, you would average the yi values for the points that fall into those neighborhoods. So this expression now for the sum of squares error, we have this j, which is the number of neighborhoods. And these y sub j hats, those are the average of the yi in each of the neighborhoods. And then we can define r squared to be 1 minus the sum of squares error divided by the sum of squares total. Just a minor note here, in 432, we will never use r squared as the metric for picking a model, although we could. I just think it's more appropriate to use root mean squared error because it's in the units of the problem, but more on that when we get to more practical applications. But r squared comes up here in a second, so I need to define it. Okay, right. So how do we stop, right? So this, if you're all familiar with computer science, recursion just goes on until you tell it to stop. So I think it should be clear, maybe we'll go back to this picture. If we just keep splitting, eventually we'd have to stop because you would have one observation in each neighborhood, right? But we don't like that. We don't want to be lonely. We want to have some neighbors, right? And also, I think you could see that would probably create a not so great prediction, right? Like that's we're hitting at this idea of overfitting here. That would be too flexible a model. Okay, so how do we stop? So we're going to use this rpart function from the rpart package in R when we go to fit these decision tree models. So it has a couple tuning parameters. It actually has a bunch of tuning parameters, but I just want to talk about two because they're going to be the ones that we consider. So min split is a tuning parameter for the number of observations that have to be in a neighborhood to even think about splitting it, right? So this might be illustrated by thinking about the extremes, right? So if you set a min split of 2, well then if you can split when there's 2 observations in a neighborhood, well then the 2 resulting neighborhoods only have 1 observation. So that means you can always split. But if you set min split higher, like you need 20 observations to do a split, well, I think if we go back here, then we would have had to stop after that second split. Maybe even after the first. Let's say min split of 15, we would have had to stop after that second split here. I'm pretty sure. I'm not good at counting. Okay. The other one is this parameter called CP, which they call the complexity parameter. So this says that so basically you have some numbers here. You often, I forget, the default is either something like, I forget, it's either like 0.1 or 0.01. I honestly don't remember, but we'll find that out when we get to R. But that's not the point. So basically it says that, like, okay, so min split, you're allowed to split. So now you found the best split in that region. Do you accept it? Or do you have to stop instead? And you only accept it if the split increases that r squared value by CP or more. So thinking about the extremes again, if you set CP equal to 0, well, then any split you come up with will be accepted. So we can manipulate both of these, and I think you can sort of see how both of them are related to growing a larger tree, but we'll illustrate that real quick. Oh, no. First, sorry, we'll illustrate that in a second. First, we're going to talk about how this actually becomes a tree, if that makes sense. So what I have here are two ways of representing a tree fit to this data set. So here I have some data with my gray points here. The dashed black curve is the true mean function, and this orange is, in R, I use this R part function, and I fit a tree to this data. Okay, cool. And now this is the estimated mean function from that fitted tree. So here is what we would call the root node. And it gives us a little bit of information. So this 100% here, that's how much data would be in that partition. But that's not super important. What's more important is this, which this is just y bar. So this is the average of all the yi values that we see. Okay, so then splits happen. So this first split happens at an x value of negative 0.52. So that is, sort of represented here. And so this yes and no tells us which way to go down the tree. Oh, here's a note. This thing on the right-hand side, we call this a tree, but I think anyone who's ever seen a tree before would say it's an upside-down tree. But I digress. Okay, so this says that, well, if you have a value of x less than negative 0.52, go this way. Okay, cool. How much of the data is in that partition? 23%, which, yeah, sure, that checks out. But importantly, what do we predict in that region? Well, this. So I'll call this mu hat in that region. So that -1 is seen right here, which is the average of the yi values for this point, this point, this point, this point, this point, this point, and this point. Okay, cool. So if we weren't less than negative 0.52, we come down this way. And this is what we would call an internal node. Okay, so, and this internal node says, well, 77% of the data is in here, and that's all of this data here. And it says, well, at that node, predict 0.59, which by my calculation is like this. Except we don't see that represented on the graph because it's an internal node. So it doesn't actually influence it influences the final output, but it's not seen in the final output. So what these three nodes are is they're called terminal nodes. You could also call each of them a leaf. And together leaves because it's a tree. But it's upside down. Anyway, so there's this second split here at an x value of 0.2. So by my calculations, that's, here. So 0.2 is about here. And so if we're greater than or equal to 0.2, we go this way. So that's over here. And that's 43% of the data. That's this data here. And we predict 0.53. So again, that's the mu hat in that region. And that's exactly this here. I'm realizing that pink is bad over orange. And then if we are instead less than, let's just say not greater than 0.2, so less than 0.2, we go this way, which is in here. I should say in here for the x values, but the data that we care about is here, which is 33% of the data, and the average of the yi values in there is 1.3. So we get this here. Blue is better. Okay, so I don't know, I've perhaps overly explained that, but I think it's important. So this tree that I built here was for some value of this min split and CP. I don't remember which, but it's not important. But let's just say we relax them a little bit, so move them closer to these two extremes that I talked about. maybe we get a tree like this. And I'm not going to walk through all of that again, but I'll try a little bit. So like, let's talk about maybe this node right here. So to get there, we have to go like that, right? So that means, by my checklist, we have to have an x that is greater than 0.81 to go this way. We have to have an x that is bigger than or equal to 0.2 to go this way. Then we need an x that is less than 0.65 to go this way. And then we need an x that is less than 0.35 to go down to here. I really hope I didn't screw that up. So let's see. Greater than 0.8. Where is that? Wait, no. Greater than 0.81, so we went this way. Greater than 0.2, so we went this. Sorry, I'm redoing this. So I'm here. Less than 0.6. Okay, so less than 0.65. I think that's that split there. But greater than 0.35, which is there. So I think that amounts to this region here. So split there and split there. Did I get it right? I don't know. Check me, but I think that's about right. Okay, so again, the region defined by going down the tree like this is given here, but ultimately it matters that it's wait a second. No. Sorry. Oh gosh, that was all wrong. So what ultimately matters is being bigger than 0.2 and less than 0.3. So I'm guessing that's between here and here. And we see that it should be negative 0.38, which that seems about right for this here. So sorry, it's the region between here and here. So these are the relevant data points. Oh gosh, I'm sorry. Okay, but hopefully you can recreate that. And again, these two graphics are in the book, so you can see how they were created, and you can check me on all that and make them bigger and redo that work there. But hopefully that's relatively clear. Okay, so moving on. Here we see 3 different trees all applied to the same data. They all have min split of 2, and they have different values of CP. So basically, in any region, we're going to allow a split, but we're going to stop depending on if it improves enough via the CP parameter. And we see that as we relax the CP parameter, that is, we make it smaller, we get, this more wiggly type thing. And here I am using that technical term, wiggle again. We can also look at this the other way, which is to say that now we're fixing CP at 0.1, 0.01, and now we're starting with a min split of 25, then 10, then 2, that is, we're relaxing the min split, and we see that as we do that, we get more and more wiggle in our estimated mean function there. Okay, cool. So I think that's all I wanted to say about KNearest Neighbors and trees. I guess one point that I didn't say about trees that we'll drive home when we do this in R in either the next video or the one after that, but is that trees have a different way of handling categorical predictors. Actually, I'll just draw this real quick. So let's say this is a root node here. So this is the root. And let's say we had a feature X in our data that had multiple possible categories. So like, let's say cat, dog, zebra. Trees have this nice feature that say, well, if we want to... That was the worst arrow I've ever drawn. If we want to split on this variable, we can say, well, dogs we send them down the left side of the tree, and cats and zebras, well, we send them down the right side of the tree. So we don't even have to convert to numbers under the hood. We just say, well, these categories go one way, these categories go the other way. That's a very unique feature of trees. It's very, very useful. I guess one more thing I should say about trees is that they are what would be considered interpretable because of this nice sort of tree that we can spit out. Like, you could give this information to a practitioner and they could probably do something with it and like make predictions based on it very easily. That's kind of an idea that we've been shoving aside, this idea of interpretability of models. We've been saying like we only care about making predictions, but later we'll circle back and say, well, what if we wanted to understand how our model is making predictions? Then we'll come back and sort of talk about the relative interpretability of our various models. But for now, we're just focused on estimating conditional means and making predictions. So we'll sort of put that off for another day. Okay, so that was our introduction to non-parametric methods. The big changes from the parametric methods that we saw previously is that now we're not making assumptions about the form of the model. And now, instead of model parameters, we often have these things called tuning parameters that we set ahead of time, but we'll see that we have to try a bunch of them and pick which ones are best. But that is sort of how we contrast them to parametric models. Okay, I've started rambling, which means it's time to end this video. As always, I should actually say goodbye. Hi. Again, as always, if you made it to the end of the video, good job, and I'll see you in the next one.